So welcome to the last lecture in this series on uncertainty. It's already almost over. There's so much more to say, but only one more lecture. So far I've only talked about uncertainty in static cases. So we have a set of points and they have maybe uncertainty, but at least they stay where they are. And in this last lecture I want to move away from this assumption and talk about uncertainty in the context of moving points. Okay, so in practice, points often don't stay where they are, they move around, and if they move around and we don't keep careful track of how they're moving, then we become more uncertain about their location. So it's the same as before. I first press the laser and then, no? Maybe I first do it once with this one, and now it works? Okay. Starting to understand the procedure. Okay, so moving uncertain points. How can we, what are they, what can we do with them? So I repeat one slide again from the first presentation to bring you back on the right page. So if I have a set of points which are moving, I want to maintain their potential location. So maybe I have a single point which moves around. So I have some point P, here's P, and P is able to move. And I know that P was in this particular location at some time t. And I know that it cannot move faster than, well, I don't know, depending on this guy, maybe he can run for 15 kilometers an hour if he really tries, but he cannot go faster than this. So this means that in one time step, P can move at most some distance d. So if I wait one time step, then P can be somewhere else, but it's certainly going to be inside this disk here of radius d. And now if I wait for t time steps, then I have some disk of radius d times d that must contain my point. Or in other words, if I knew where P was t time units ago, then I know that it now exists somewhere in a circle of radius d times d. Okay? And now I want to consider this question of, or this model in which I'm allowed to query the location of a point. So I have some set of moving points. For each point, I knew its location at some point in the past, which means that right now I have one disk around each point which contains their current location. I just don't know where in each disk these points are. So these disks we can see as uncertain points in the disk model. But because this uncertainty comes from motion, if I wait for some time, these regions grow. Okay? Every unit of time that I don't do anything, I become more uncertain about the locations of these points. So these disks become bigger. But in this model, I'm allowed to get more information about my points by asking one point, hey, can you please tell me where are you exactly? And we assume that these points are able to measure their own locations with exact precision, or maybe not exact, but with some other uncertainty. But let's assume for now they can measure their own locations exactly. So I ask one point, where are you? And it returns to me, well, actually, you thought I was here, but I'm actually somewhere else in this disk, namely I am here. And now I know with precision, with zero imprecision, where this point is. But while I did this, all the other regions grew because it took some time to ask this question. Okay? So, and I can do this again, and maybe I want to distinguish these points as well as possible. So I see, well, these two guys are overlapping in their circles, so I want to query one of them to distinguish them better. And I try to query this guy, and now I know exactly where he is, but now two other regions start overlapping. And suppose that I'm interested in the question of how to separate these uncertainty regions as well as possible by doing these kind of queries. So it's like this game where you have a bunch of, I think it's moles or meerkats that are sticking out of the ground, and you can hammer one, but then it pops up somewhere else. And you can never have them all flat. It kind of feels like this. So in which order should we query these points to separate them as well as possible? That's the question I want to consider. Okay, so to make this a bit more precise, querying moving uncertain points, I will define the concept of ply. Okay, so if I have a set of regions in the plane, like this, and I'll assume they are disks because that's what the uncertainty regions look like in this case, but for the definition of ply, they could be any regions. Then the ply of a given point is the number of disks that the point is contained in. Okay, so if I have some point here, then it has a ply of 1 because it's contained in one of the disks and not in any of the other disks. And this point here is contained in 3 disks, so it has a ply of 3. And now the ply of the whole set of regions is nothing else than simply the maximum of the ply over all points in the plane. Okay, so I take the maximum of all my points, and then I find there's one point which has a ply of 4. It's contained inside of 4 disks, and there's no point with higher ply, so the ply of this set of regions is 4. Okay. I'm going to claim that low ply is good in many applications. So for example, if you think back to the third lecture I gave about preprocessing, often you can preprocess a set of regions for computing something efficiently if the regions are disjoint or if they have low ply, but not if they have high ply. Also, just intuitively, if I want to distinguish the locations of these moving points or minimize the potential of car crashes or anything, I want this ply to be low. And ideally, I would want the ply to be 1, so all the regions are disjoint. But if this is not possible, I want to have the ply as low as possible. Okay? So I'm going to analyze this algorithm in a competitive sense, but I think I can go through this slide pretty quickly because Sue already talked about competitive analysis in one of her lectures. So just to recap, classical offline algorithms first receive an input. Online algorithms receive a sequence of input events and needs to react to each event before knowing what the next event will be. So you, instead of being able to look at the whole input at once and computing something optimal, you have to compute things on the fly as you are receiving more information. And you can analyze such algorithms using the competitive ratio, where you're comparing the performance of your online algorithm to some optimal offline algorithm, which might have received the whole input at once and done the optimal thing. If you can do something that's close to what the optimal offline algorithm could have done, then we say the algorithm has a low competitive ratio, which is a good thing. Okay? So now I can state my problem. I'm given as input a set of n moving points with some set of initial regions. So the initial regions depend on when I last measured those points. Okay, so they are this set of disks in the plane. I have some target time t star. At time t star, I want to have separated out my regions as much as possible. So I want to have a low ply of my set of regions at time t star, which is some units of time into the future. And the objective is to select one region in every time step. And if I select one region, I query this point, and I get as additional input the location of the point at that time. And all the other regions will grow by 1. So I get a sequence of input of data elements in this way, But of course, what I get also depends on what I decide to query, which depends on what I got before. So it's an online algorithm in this sense. I want to minimize the apply of the regions at time t star, as I said. And I want to design a strategy of choosing which point to query that's good in a competitive sense. So I want to compare against an adversary algorithm that knows in advance exactly how all these points are going to move through time. So it knows at every time where the point will be if it would query the point at that time. But it still has to simulate what we can do. So the adversary still has to do one query at every time step and grow its regions. Otherwise, it would not be fair to compare against. But it knows the trajectories in advance and can design an optimal query strategy for this set of trajectories. Whereas we don't know the trajectories, so we just have to choose something based on the limited information that we have. And if we can get within maybe a constant factor of such an optimal algorithm, then we've done a good job. Okay? So this is the goal of the problem. Okay. So before I give any result or algorithm to do this, let's talk about projected regions. So it's useful for this problem to look at the uncertainty regions in a slightly different way. Keeping track of this set of regions that grows all the time is a bit inconvenient. And since we know that we're only interested at the result at some given time t star, we can project our regions to this time t star. So if we look at the points in time space, so a three-dimensional space where we have two dimensions which correspond to our spatial dimensions and one dimension which is time. I'm going to draw time vertically. Then my points are somewhere floating in this space. So a point at a certain point in this three-dimensional space means that I knew the point was at this location in space at this point in time. Okay? So if the point is somewhere higher, it means that I knew where it was longer ago. If it's lower, then I knew where it was more recently. So these points float in space, and I can project their so I know that they're going to follow some trajectories. Okay, so they move through time. Time moves from top to bottom, and these points move around in space. Of course, these trajectories cannot go back up because you cannot move back in time. And they're going to end up somewhere at some time in the future, at time t star. But because I have this limit on their speed, I know that these trajectories must lie inside some cones. Okay, so I can draw a cone centered at each point in space-time, which is a cone that moves down with an opening angle depending on the speed limit. So it's d if we assume that they can move at most d in 1 unit of time. Well, the slope would be d. So I get these cones, and I know that these trajectories have to stay inside the cones. So in particular, I know that at time t star, we get some horizontal plane. So this plane here is time t star. I know that at time t star, they're going to end up somewhere in the circles that I get by intersecting these cones by this plane at time t star. So maybe right now I'm at time t, somewhere above here. And I know that right now they're in some smaller circles, but I can say that at time t star they will be in these bigger circles. And now as I move through time, I have the advantage that I don't have to update these circles because these projected circles stay the same for any point that I don't query. And if I do query a point, then it just means that the circle becomes some smaller circle. Okay? So I call these circles the projected uncertainty regions. And in this model, if I do a query on one of these circles, then the circle doesn't become a point. It becomes a smaller circle, depending on how much time I still have left until time t star. But all the other circles stay where they are. Okay? So this is somehow an easier way to think about what's going on and to design strategies to solve this problem. Okay, is this, yes?
When the circle shrinks, the point you're querying, the center of the circle will...
It will change, yes. Yeah, the new circle will be centered at the current location of the points that you get back from your query, yes. Yeah, but it will be contained inside the circle that you had before, because you get more information about this uncertain point, which describes the location of P at time t star. Okay. All right. So we have this this model of these circles, and you can point at one, and then it will shrink a bit, and you can point at another, and it will shrink a bit, and we want to minimize the ply at time t star. So what can we do? Well, let's just try a few maybe obvious strategies and see how they perform. So attempt number one. Let's just always query the region which currently has the largest ply. Maybe it makes sense, right? If we have, we want to minimize the ply at the end. If there is some region which has a high ply, so it contains some point of high ply, then maybe we should just query that region, and we'll hopefully get a lower ply, maybe. Okay, so let's see what happens. So I have a set of regions here. I look at the current ply. So I look at every region, and I mark how high its highest ply is. So this region doesn't intersect anything, so its ply is 1. This region here intersects several other disks, and in particular it has this location here where 3 disks overlap. So this disk will have ply 3, and also the other 2 that contain this point, and these disks have ply 2. So if I want to query the region with the largest ply, I pick one of these 3. So there's multiple of them. Well, let's just try one. Maybe I query this region here. Okay, and then I reduce it, and now the ply became smaller, and looks like a good thing. Okay, the claim is that the resulting ply delta after doing this strategy until time t star can be a factor n larger than the optimal ply that our adversary can achieve. So it's not a good strategy. Okay, so why not? Well, consider this example here. We have a bunch of regions, and all of them overlap each other. So they all have the same ply, namely 9, if there's 9 points, because they all contain this point here in the middle, which is contained in all of these circles. So we pick any circle, and we shrink it. And now we do the same thing, and we pick any circle, and we happen to pick the same one, and we shrink it, and we do the same thing. We pick any of the circles, we happen to pick the same one, and we just keep querying the same region over and over again. And it keeps containing this point here. So obviously, it's not a very good idea, and in the end, we still have this point. If this moving point happens to move towards here, then we could still have a ply of 9 in the end, while maybe the optimal strategy would have been to query everything, and we would have had a nice disjoint set of regions. Okay, so there's something wrong with this strategy, even though intuitively the idea makes sense. If something has high ply, then we want to query it. Okay, but what was wrong here? Well, we kept querying the same entity all the time. So maybe we should not do that. So let's think of another strategy attempt. Why don't we just always query the currently largest region? So if we query the largest region, then it becomes the smallest region, and then there's a different region which is the largest one. So we will never keep querying the same region all the time. In fact, we will never query the same region again until it becomes the largest one again. So maybe this is better. What do you think? Is this better? No? No? So it is a little better than the other one, but it's still not very good. So So to illustrate what happens is we pick the biggest one and we shrink it. And so we will never query the same one twice until we've queried everything else. So effectively, this means that we're choosing a cyclic order and just querying the regions in this one cyclic order all over all the time. Okay, so if we do this, then the final regions at T star will have sizes 1 to n, which is the optimal distribution of sizes you could have. However, the configuration depends on the order in which we did this query, and if we just start by querying always the largest region, then this order is effectively random. So it could be a very bad order. And in fact, I claim that the resulting ply here, so it will not be a linear factor bigger than the optimal ply, but it can still be a factor square root of n bigger than the optimal ply. Okay, so why is this? Well, consider this configuration. So my points are nicely lined up in a line here, and the distances are integers. So these two have a distance of 1. They really like each other. This is 2 and 3, 4, 5, 6, 7, 8, like this. Okay. So in the optimal solution, I'm going to end up with these uncertainty regions. So every point is inside some region of, and the regions will have sizes 1 to n, right? Because I queried them cyclically. And our adversary, who knows that this is the final configuration, decided to query them in this order. So first this one, then this, 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 then this. And this is what we end up with. However, if we were unlucky and we chose the wrong order and we queried them in the other direction, then the picture looks like this. So the largest disk is here, and the second largest is here, and the second largest is here. And here we have some very small disks which are very far spread apart. But here we have many large disks that overlap each other. How much do they overlap? Well, if you do the math, then it will turn out that there's going to be one point here with a ply of square root n. Okay? So it's better than n, but it's still not really good. Okay. So in the first strategy, we had the idea of querying regions which have high ply. In the second strategy, we had the idea of querying large regions first, or not querying the same one all over again. And both of these things make sense, but we need to somehow combine them to solve the problem. So I'm going to present a third strategy, and this one is going to work. So what we do, maybe it looks a bit strange in the beginning, but I will try to explain why this works. So first, we keep doing the cyclic querying that we did in the second strategy until tau, so tau is the amount of time we still have left, is equal to n. Okay, so as soon as I have only n time steps left, I will stop doing the cyclic query. And I assume that I have enough time in the beginning to be able to do this at least once. So at time tau, I'm going to have n disks, and the radii of these disks are going to be n plus 1, n plus 2, n plus 3, up to 2n. Okay, they're going to have distinct integer sizes from n to 2n. Okay, so if this is the input, then I do this until this is the case. Okay, so now the regions have sizes, well, n plus 1 to 2n. Now, I'm going to have a while loop in my algorithm. So while there are still any regions left, I'm going to divide them into two groups. So I find the half of the regions which together have the highest ply. So for every region, again, I measure the ply like before. So just 1, 2, 2, 2, 3, 2, 3, 2. And I separate my set of regions into two sets. The set which has the highest ply and the set which has the lowest ply. Okay? So all of the plies of these regions are at least as big as all of the plies in these regions. Okay? Then for the set of high ply regions, I'm going to query all of them exactly once and in any order. I don't care about the order, so maybe from large to small, but it doesn't actually matter. I just query all of them once, and they become smaller. And the other half I just don't query. Okay, and now, so I throw away the others out of my set. They had low ply anyway, so I just don't bother ever querying them. I throw them away. And the ones that had high ply, I queried exactly once. And now I set my n to be half n, and I'm again in this situation. So the sizes are again n plus 1 to 2n, but now for a smaller value of n. And the amount of time I have left is again n. So I'm again in this situation where tau equals n, and the regions have sizes n plus 1 to 2n for a smaller value of n, which means I can now recurse on this strategy. So while there are still regions left, I do the same thing. So I pick the half of the regions which have the highest ply. So these two have ply 2, the others have ply 1. These two I query, the other two I throw away, and I repeat. Okay, so then in the end, this is the set of regions that I'm left with. So these were the ones I threw away in the first step, these I threw away in the second step, and these two were already disjoint, so I just stopped, but I could, of course, have kept going. Okay, so this is the algorithm. So clear what the algorithm does? Okay, so my claim is that with this strategy, the resulting ply is within a constant factor of the optimal ply. So this actually works. It gets a constant competitive ratio. Why is that the case? Okay, so the algorithm or the argument is somehow a geometric argument. I'll try to explain at least the main idea behind it without going through all of the tedious mathematical details. But still, I need to introduce a little bit of notation here. So let's say R is my set of n regions, and they have these sizes n plus 1 to 2n. Okay, so this is R. S is the optimal final regions. So if I knew where those, what the trajectories of the points were, and I chose some optimal strategy based on this, I got this set S. So this is what my adversary can do. It knows that if it does the optimal thing, then I get this set of regions S. And obviously, every region of S is contained in one of the regions in R, but and they have sizes 1 to n, but I don't know in which order. H is the ply such that half of the regions in R have ply at least H. Okay, so H was, so remember in the first step I said I keep the half of the ply of the regions of high ply, and I throw away the regions of low ply. So there's some value of the ply, that's the cutoff value between high and low ply. I call this value H. Delta prime, no, is this a prime? Is this a star? Delta star is the optimal ply. So the optimal ply means the ply of S. Okay, so delta star is the ply that the adversary will obtain. R prime is the half of R with high ply, so it's the half that I'm going to repeat querying. So this is R prime. This was the whole of R. S prime is just the part of S that corresponds to R prime. And now I'm going to put some grid on top of the whole construction. So Xi is going to be a grid of cells which have some size that is a constant times linear. So I'm going to put this grid onto the whole space. It's a grid Xi, and the size of one grid cell is somehow roughly n by n. So these regions cover some constant number of cells. Okay, this is the notation. You remember all of this because it won't be on the next slide. Good. So now for the argument. I want to show that the ply that we get by this argument is somehow a constant times delta star. So first, notice that S prime must cover an area of at least omega n to the third divided by delta star. So why is this? Well, remember that the sizes of the regions in S prime all have to be different. So on average, they have to have a linear radius, which means that the area they cover must be roughly n squared. So the total area that all of these regions in S prime cover must be roughly n to the third. However, they might overlap each other, but they cannot overlap more than delta star, because this is the ply of the final result. So the area that is covered by these purple disks here in S prime is at least n to the third divided by delta star. Right? Okay. Now, notice that S prime intersects at least omega n over delta star cells of Xi. So why is this? Well, because they have to have an area of this n to the third over delta star, and every grid cell has an area of roughly n squared, so they must intersect n over delta star cells of the grid. Yes? Okay. So these are the cells that are intersected by my set S prime. Okay. Now, within this set of grid cells, I'm going to look for an independent set of grid cells, which are all intersected by S prime, and which still have n over delta star elements. So I'm going to say two cells are independent if they are far enough apart that they cannot be intersected by the same region. And because the regions have at most linear size and the cells have a linear diameter, this means if I have some constant distance between two cells, they're going to be independent, and therefore I must have a constant fraction of my cells in a maximum independent set. So consider such an independent set I. So I is a set of cells that are intersected by S prime and which are independent, and I claim that I still have at least n over delta star of such cells. All right? Now, each cell of I is intersected by at least h unique regions of R prime. Okay. So why is this? Well, each cell of I is intersected by at least h unique regions of R prime. That doesn't make too much sense to me. So what am I trying to say here? Let's see. So I think the cell H is not intersected by the cell of I is not intersected by H regions of R, but there are at least H regions of R that are within constant distance of such a cell. So why is this? Well, the cell of I must intersect one cell of S prime, and this cell of S prime is contained in some cell of R prime, but every cell of R prime had ply at least H, so there must be at least H regions that are within constant distance of this cell I. Okay, so intersected is maybe a bit too strong word here, but they are within constant distance of H unique regions of R prime, and by unique regions I mean the same regions will not contribute to one of these other cells. So I have n over delta star of these grid cells, and each of them have H regions of R prime that are assigned to this grid cell, which means that there must be at least H times n over delta star regions in R prime. Okay, because for every of these grid cells I can find some set of H regions that I can assign to this grid cell. So R prime must contain at least H times n over delta star regions. which means, in turn, that h must be O of delta star, right? If I know that I have at least h times n over delta star regions in R prime, but I know that the total number of regions in R prime is n over 2, right? It's half of all of my regions, which means that h and delta star have to cancel out in this formula, which means that h must be at least delta star. Okay? So in my strategy, when I pick the high ply regions and I throw away the low ply regions all had a ply that is less than h. So they all had a ply that is less than delta star times some constant. So I can safely throw them away and never have to worry that I throw away something with a ply that's too high, because it's within a constant factor of the optimal ply that we can get anyway. Okay. And this argument continues. I do the same thing recursively on this set, and at every time, every phase, I set aside some set of regions which have a ply at most a constant time times the optimal ply, and therefore the strategy achieves optimal ply in the end. Any questions about this argument? Okay, so this is well, a way we can query these regions in the right order as to minimize the ply at the end, and this is just some first result in this model of uncertainty and motion, and I think there are many other interesting questions you can ask in this model which have not been studied yet, and it will be very interesting to see if similar results are possible there. But that's not what I'm going to talk about for the rest of the lecture. I want to switch topics a little bit to storing moving uncertain points. Okay, so we have moving points which cause uncertainty, and now I'm not worried about how I obtain these moving points or how to query them. I just assume that I'm somehow in a situation where I have a set of points that are moving and that are uncertain, and I want to somehow keep track of them. I think a natural question is, how can we store these things in a data structure and maintain changes to their imposition, maintain changes to their location, and still be able to do useful queries about this set of points. So for this problem, again, I'm going to start with maybe the easiest question I can ask. Okay, so P is a set of points in the plane. So these are now precise points. And Q is some sort of a query point. And I want to ask some question about Q and P, and I think the simplest question I can think of is it maybe true that Q is an element of my set? Okay, so in the precise case, there are two possible answers, yes or no. So yes, Q is in my set, or no, Q is not in my set. Okay, the only possible answers. And we can answer this question in linear time by just comparing my point to every point in the set. But if I expect to be asking this question a lot of times, then I can do better by storing my set P inside some data structure that allows me to answer such queries in logarithmic time. Okay, so this is a point location data structure. For example, we can build a Werner diagram and build a point location data structure on this subdivision, and then for every query, just verify whether my point is equal to the center of the Werner cell. There's one way to do it. There are many ways to do this. Okay, so is this point equal to this point here, yes or no? You can answer this in log n time. Okay, so now let's move to the uncertain case, so imprecise case. So I have a set of imprecise points, and I'm going to model them again as regions. I'm given a region, the real point is somewhere in this region. Well, we've seen this model many times. and R is a set of such regions in the plane. Q is a query point, and I'm going to ask the same question. Is Q an element of my set of uncertain points? Yes or no? Okay. Is Q an element of P? So now there are again two possible answers. The possible answers are maybe or no. So I can never know for sure that Q is an element of my set because I don't know where the points in my set are. But I know for each point that it's inside a certain region. So if I want to know if Q is one of these elements, I have to know whether Q is in one of these regions or not. Okay? So again, we can answer this question by storing the regions in a data structure and doing point location. Okay? So is my query point in a region? Then I answer maybe. If my query point is not in a region, then I answer no. Okay? So far, nothing very exciting. But now, let's assume that my points are not only imprecise, but they're also dynamic. Okay, so for example, because they were moving points and their imprecision was growing because I did queries and I had these disks which sometimes shrink and sometimes grow or move. And I'm not worried about how to query them. I just get this set of disks and I have to somehow deal with it. Okay, so I have a set of uncertain points, and every point is inside some region, and our estimate of the location of this point might change. So I might get more information about where the point is. Or the real location of the point may change, which means I have suddenly less information of where the point is. Or in other words, the uncertainty region grows. Okay? So now let R be a set of n such dynamic uncertain regions in the plane. So I have some set of regions here, and they keep shrinking and growing and moving. And again, I have some query point, and I want to know, is Q an element of P? Is Q in my set? So again, I need to test whether Q lies inside one of these regions or not. Okay? So this question we can still answer in logarithmic time after preprocessing. So I can build some point location data structure on these regions and ask for where my query point is, and then I get an answer in logarithmic time. However, because the regions are now moving, we need not a static data structure, but a dynamic data structure. We need to be able to handle changes to my set of objects. Okay? We need to handle updates. So an update is moving one of these regions, or shrinking it, or growing it. Okay, so how do we do this? Well, there's a very large literature about dynamic planar point location. It's a topic that has been studied for several decades. So let's just look at what's out there in the literature to see if we can use any of it. So it turns out that you can support log squared n queries with logarithmic updates, or log n queries with log to the 1 plus epsilon updates. In special cases, you can even do log n queries and updates at the same time, but this is not for general subdivisions. It only works, for example, in monotone subdivisions or rectilinear subdivisions. So for certain special kinds of subdivisions, you can get logarithmic queries and updates at the same time. But you cannot do better than logarithmic updates and queries. So updates always take at least logarithmic time. And why is this? Well, basically because an update could be throwing away region and inserting a new region. And to insert a new region, you first have to do a point location to know where to insert it. And point location queries have a log n lower bound. Okay, so we can never do queries faster than log n time, and therefore we also cannot do updates faster than log n time. So actually, whether there is a log n query and log n update dynamic data structure for planar point location is still an open question. It's one of the long-standing open questions in computational geometry, and it would be very interesting to solve this. Sorry? Yes.
One assumption can be that when the regions dynamically change, also they don't overlap. Because if they can overlap, all log n, we cannot guarantee all log n for propagation.
Mm-hmm. Yes, this is a good point. So if many regions would overlap the same point, then we would still have to, well, we could find out maybe whether the point is in some region, but if we also want to report the set of regions that it is in, then we need time proportional to the set of regions to report all the regions. I'm going to assume for now that that the regions always stay disjoint, just for simplicity. Okay, so log n queries and updates is an interesting open question, but the point I want to make is that there's this lower bound of log n on both queries and updates, so we can never hope to do anything faster than log n queries and updates for the general planar point location problem. However, in our case, the bottleneck is the point location itself takes log n time, but in our application we have these uncertain regions, and yes, they change, they may shrink a little bit, they may grow a little bit, but we don't really do an update where we throw away a region here and we reinsert it here at the other side of the world. These updates on the uncertainty regions are somehow local. And if they're local, well, then maybe we intuitively might be able to handle them faster than in log n time. Okay? So this is going to be our goal. Can we design a data structure for uncertain points which supports logarithmic point location queries, but which can handle these updates somehow faster than log n? So ideally, maybe in constant time, but anything faster than log n would be interesting because it breaks this lower bound that would hold in the general case. Okay, so the problem is maintain n regions in the plane such that we can insert new regions in in logarithmic time. We can remove regions in logarithmic time, and we can locally alter or update a region in less than logarithmic time and still answer point location queries in log n time. Okay, that's the goal. So of course, whether this is possible kind of depends on our definition of local. So we need to make this more precise. So what is a local update? Well, we're going to say that an update is local if we shrink or grow a region by at most some constant factor. So maybe I make a region twice as small or twice as big. If I make it smaller, it has to be contained in the previous region. If I make it bigger, it has to contain the previous region. But I cannot shrink it by an arbitrarily large factor, because if I could do that, then I could simulate arbitrary updates by growing my region to the entire world and then shrinking it back to another point, and then I would have my log n lower bound again. So this is not allowed. But constant factors, while staying in the same location, they should maybe be possible. Okay, and also regions are allowed to move a constant time their current size, and this is somehow you could also simulate this by just growing a region by constant fraction and then shrinking it by constant fraction, but we might as well call this an atomic operation because it's somehow natural. So a region can move some distance proportional to its size, but it cannot move arbitrarily far. Okay, so in particular, large regions are allowed to move more than small regions. Okay, regions are also allowed to change their shape as long as they're fat, but maybe for now we'll assume that they're just circles, but in principle the approach can also handle any fat regions, but not arbitrarily skinny regions. Okay, one more assumption: the regions are disjoint and they stay disjoint. And this is not a very nice assumption, because in practice they're probably not going to stay disjoint, and actually generalizing this result to the case where they are overlapping is currently some work in progress. But for now, we have to assume that they're always disjoint. Okay. Yes.
I think we should have an assumption about the distance of the regions. The assumption you said in previous page, because if we have no assumption for the distance of the regions, we cannot guarantee the assumption.
Sorry. So which assumption?
The assumption about the distance of the regions.
This one.
We have no assumption about the distance between the regions in this case.
Mm-hmm.
I don't understand that we should have assumption between for the distance between the regions or not.
No, so there's no assumption on the distances between the regions. We're just assuming that well, in the definition of a local update, we say update is local if they don't move more than a constant fraction times their size. And here we are assuming that the regions are and stay disjoint, so we assume that they don't do an update which would cause them to become overlapping. Okay, so it's an assumption in the set of events, that assumption about the set of events that we have to process. And it's not a very realistic assumption, but at least it's an assumption that we can start with. Okay. So the results that we managed to obtain so far are as follows. So in the one-dimensional case of this problem, we can solve it well. Except for this disjointness assumption, we can achieve the best result that we can hope for. So we can build a data structure that can handle queries in log n time, insertions and deletions in log n time, and local updates in constant time. Okay, so we can do any of these local updates: shrink by constant factor, or grow by constant factor, or move a constant times your length in this case. All takes constant time, as long as they stay disjoint. And in 2D, we can generalize this result and get log n queries and log n insertions and deletions, but the local updates are not constant. They take log n over log n time, but still it shows that we can break this log n barrier, and we don't know whether this is optimal, so it may be possible to also get this down to constant, but the problem gets much more complicated, so we don't know if this is true. And again, this assumes the regions stay disjoint. So maybe I will briefly try to explain the one-dimensional case, and I don't think we'll have time to go into the details of the two-dimensional case, but at least it gives some idea of the type of approach you can take to solve this kind of question. Okay, so in one dimensions, my regions are intervals, right? It's the only shape a region can have in one dimension if it's connected. So I have a set of intervals that live on a line, and now I am allowed to move these intervals around. Big intervals can move very fast, but small intervals can move only very slowly. So what I could do is move this big guy this way, and the small guys stay where they are. And big guys are allowed to jump over the small ones if they move constant times their fraction. Okay. So you might say, well, this may be not very realistic. How can they jump if they have to stay disjoint? In one dimension, it's not really possible. But in two dimensions, it is possible because they would just move around, and somehow if we want to solve the one-dimensional problem, to prepare for solving the two-dimensional problem, we have to take this situation into account. So that's why we allow intervals to jump. But they cannot land on top of each other, so at every time step we have disjoint intervals. Okay, so how do we maintain such a set of moving intervals, or shrinking and growing intervals? Well, we need a structure that provides quick access to similar places. And by similar places, I mean places that are close to us, so that we could move to in a constant number of updates. But also, it has to support some sort of a binary search, because we want to do point location, and point location in a set of intervals is just searching in a sorted list. So I have to do some sort of binary search on this order of the points. So the idea to combine these two things that we need to do is to maintain two trees on this sequence of intervals at the same time. So here we have our sequence of intervals, and I'm going to put a space tree on one side, and the space tree will give us this first functionality, and I'm going to put a data tree at the other side, which will give us the second functionality. Okay? So basically, the idea is that the space tree will give us constant time updates, and the data tree will give us logging queries. But of course, they have to be somehow interconnected, and if I do an update, then I may have to update something in this tree as well. So what are these trees going to be? Well, for the space tree, the idea is we can use a quad tree. Okay? So remember what a quad tree is. In one dimension, a quad tree is more like a bi-tree because it subdivides an interval into two equal length intervals. But I'll just call it a quad tree because I think it's more clear. So we consider our set of intervals, and we consider the midpoints of those intervals, like so. And on this set of intervals, I'm going to build a quad tree. So how do we build a quad tree? Well, we take a root box of the quad tree, which contains all of the points. As long as there's more than a constant number of points in my root box, I subdivide it into, in this case, two equal size smaller boxes, like so. And each of these smaller boxes will contain some subset of the points. And I keep doing this until all of my leaf boxes contain only 1 point. Okay, so this is just the one-dimensional version of a quad tree. Okay, and then because a quad tree this way may have superlinear size, we have to compress it. So we use a compressed quad tree, which basically deletes any of these long empty paths. So this is what the quad tree looks like. And inside this quad tree, I also add some extra pointers, which connect neighboring nodes like this. And now the idea is that if I have some points in this quad tree, then I can quickly move to another location where the point might move to, in the sense that if my point is in a big interval, then it's going to be stored somewhere in this quad tree at some level of roughly the size as this interval, and I can move constant fractions times this length to the left and the right in constant time. Okay, that's the idea. And for this, we prove this lemma, which says no leaf is much smaller than the interval it stores. So it cannot be that we store a point in a very small leaf. Well, why not? Because if there was a very small leaf here, then it's contained in this very big interval, but it's small because it has a small neighbor, and the only reason it would have a small neighbor is if the parent box was subdivided, and it would only be subdivided if there were 2 points, but it cannot be 2 points inside one of these intervals because they're disjoint. Okay? So every interval is stored in a leaf that's roughly of the same size. Okay? And now for our data tree, we need to still be able to do logarithmic queries. So we need some sort of a balanced binary tree. So we just maintain a balanced binary tree. Okay, so for example, a red-black tree or AVL tree or whatever your favorite search tree is. We build it on this sequence of intervals here. Okay, so how do we do it? We just take neighboring nodes and we connect them together until we have some balanced tree. And this balanced tree has logarithmic depth, okay, because it's balanced. So this means that for a query, we can now just follow a path in this tree and find the interval that contains our query point in logarithmic time. Now we connect these two trees together. So we have the leaves of the space tree and the leaves of the data tree, and we connect them if they're contained in each other. And okay, so how do we handle the query? Well, it's fairly easy. We have a query point, and we just follow some path in the bottom tree until we find the 2 points that are the neighbors of this query point, and now I just have to check 2 intervals, whether they contain a query point or not. And I find yes, it contains a query point. And how do we handle an update? Well, for an update, suppose we have this interval here that we want to update. We look at the location in this data tree, and now we look at the new location, which must be somehow a constant, in a constant size neighborhood of this node in the data tree, and we simply walk through the tree to find the current node that contains the location where we want to store the new point. And there we just add a new leaf that contains the new point, and we connect it, and we throw away the old leaf. So, okay, we throw this one away, and then now I also need to add this point into my other tree. So how do I find the place where I had to add it? Well, I can just look at my neighboring points that are already in this tree. So from this new node, I just walk in constant time to my neighbor, and now I walk down the tree until I'm in the other tree, and now I find some place where I can add this new point. Okay? And this all to constant time. So there are some some small issues here that I'm ignoring. So it could be that by inserting something in this balanced tree, I have to rebalance the tree, right? You know, trees have to be rebalanced, and then rebalancing may take logarithmic time. However, if we observe that if we do a bunch of these updates in constant time each, then if we don't actually rebalance the tree until we do another query, then we may have a somewhat unbalanced tree, but the total depth of the tree will still be logarithmic. And if we ever do a query, then we can rebalance it. And if we never do a query, then we can simply rebalance the tree after we did a logarithmic number of updates, and we still get amortized constant time. And also, there's some issue where the path in this tree down to the neighbor might be too long, so it wouldn't take constant time. But for this, we can add some extra auxiliary pointers. So there's some details that have to be worked out to really make this work. But this is the rough idea. And I think I will not talk about how to do this in R2 because I'm out of time. But maybe just to give a rough idea what it looks like in R2. This is what it looks like: space tree, data tree. We again built a squad tree, but and we want some data tree, which is a point location tree. But now we have these problems that we have to deal with, like updates are too costly. We have to maintain this auxiliary tree and another tree on top of this tree. And we have another problem, which looks like this, but we can also solve it. And then we get something like this, and we have another problem. And we can also solve that problem. But don't worry, be happy. In the end, we can solve everything like this. And we add another structure on top of this, which looks like this. And we built actually 4 of them. But and then we're done. Okay. So that's how to do it in 2D. And unfortunately, this doesn't give constant time updates, but n log n over log n updates. Okay, any questions about this approach? Maybe questions about the one-dimensional case. Yes?
In the part about the flies,
Mm-hmm.
did you consider the strategy where you would query the disk that's contributing to the most to the total flies, or just the disk that intersects the most other disks?
The disks that intersects most other disks?
So it's contributing to the fly count of several dimensions. Something that could look bad in this case.
Yeah, so it's an interesting question. So in this result that I presented, we were trying to minimize the maximum ply. So if there are many locations where we have a certain ply that's almost as bad as the maximum, then we don't measure that, so we only measure the maximum. So I think in this case, this strategy, right, in this case, this strategy might not give any good results. But actually, another version of this question that is currently work in progress is not to just measure the maximum ply, but somehow have some measure of the total amount of ply, or the way we measure it is actually the number of possible order types that a point set can still have given a set of regions, and then you take the logarithm of that to get something measurable. And there you want to balance out having single places with a very high ply with many places which have a lower ply, but which still could contribute more to this measure of the total amount of confusion, I think you could call it. And there something like this might make sense, but we don't know yet. It's not. It's still an open problem. Any other questions? Okay, if no more questions, then thank you all very much for your attention, and thanks for inviting me. It was a very nice experience to give this series of lectures about uncertainty, which I think is a very interesting topic in computational geometry, and I hope I've convince you that there are many interesting problems, many interesting results, but also still many more problems that have not been solved and that are very worth studying. And thank you for your attention.